What is this word? Huh. Hmm. Got a little distracted. All right, all right. I think I could convince myself to move on. All right. Hilbert series of second-order jets of determinantal varieties. Didn't I just see something like this? SO of omega x is not 0. I don't know what that means. SO is an interesting one. Yeah, I don't know what that means. I'm tempted to look at this just to see what... Oh, it's probably something about... I think I actually do know what that is. Okay, no, maybe I'm not sure. I was going to say maybe it's something to do with the... like, asymptotics of the canonical. But apparently, it's just a subvector space of the global sections. Which is, I can kind of pull this over here. I don't want to, I have to. So it's just this intersection of the images over all E, this F push forward of E. And to here, but this is Cartier operator. So I was wrong. Degenerations of maps to projective spaces. This kind of sounds interesting. Depending on how like easy it is to compute these polynomials, or like how canonical these polynomials are. I think that I'm not exactly the right audience. I'm like certainly not the right audience for that, but it sounds neat. In this paper, we initiate the systematic study of density of algebraic points on surfaces. We give an effective asymptotic range. I'm kind of wondering what that means to some extent. It's like initiate the systematic study of density of algebraic points on surfaces. So something about the degree maybe, or some kind of complexity. And then also density. So it's in some, either like some ball or maybe with some fixed height or something. I don't know if that last sentence made sense, but we give an effective asymptotic range in which the density degree set has regular behavior dictated by the index. The density degree set. So like the degree of density, we give an effective asymptotic range in which the density degree set has regular behavior. By contrast, in small degree, the question of density is subtle. It depends on the arithmetic of curves. That makes sense. I can imagine that you could have a surface where there's like, for example, one fiber and it has effectively like all of the rational points. Or like some surface maybe not exactly fibered over something else, but maybe like birationally fibered over something else. And kind of, so I can imagine that there's a surface where there's like a finite number of curves that contain all the rational points. That's all I'm saying. It's not very interesting to say, but small degree, by contrast, in small degree, the question of density is subtle. It depends on the arithmetic of curves. I believe that. Also the small degree part. Just because I bet like somehow, right, like I have no idea what this paper is going to be about, but I can imagine like some curves of low genus have like a bunch of points of some small degree, like quadratic points. I imagine like P1 and genus 2 curves have just a crazy amount of quadratic points. So depending on those sitting on your surface, I can imagine that changes how you could get a result. But we give several explicit examples displaying these different behaviors, including products of genus 2 curves with and without dense quadratic points. These results for products of curves have applications to questions about algebraic points on closely related surfaces, such as rank growth on abelian surfaces, by elliptic surfaces. I am curious, like, what the main statements are in this paper. I said earlier there's a paper that wasn't up my alley. I think this one is like much more related to something that I've thought about before. So I would say like more up my alley in terms of things that I've thought about or would want to think about. Smooth projective geometrical connectors, nice variety. We write delta for the density degree set of X, the set of natural numbers D for which the closed points of degree D are Zariski dense. Okay. We denote by n the set of all positive integers. Okay. For a nice curve of genus G, the structure set is known to reflect the geometry of C. Sure. For instance, the minimum of this is related to the gonality, right? I was going to say, Isabel has a lot of... Maybe she has got one paper on the gonality and its relation to what they call... I thought it was called the arithmetic degree or something like that. So the density degree set, it intersects... the density degree set intersecting those natural numbers of greater than or equal to twice the genus is equal to the index. Intersect. Oh, that's kind of an interesting result, right? But this is probably saying that there's some bound between like the gonality and I guess something depending on the degree or the index. But this is a nice way to say this, I think. Actually, do I even understand this statement? It's saying that the set of natural numbers for which closed points are Zariski dense is exactly the multiples of the index greater than or equal to twice the genus. I think that's believable. I think the thing that I'm tripping up about is that, like, there are these weird examples of, like, surfaces. I want to say like a cubic surface where you can have like index 1, but there's like points of degree 2 and points of degree 3, but no points of degree 1. Forgive me if I'm getting that wrong, but there's definitely some examples of varieties that have similar properties. Index 1, but no rational points. And so it's kind of a strong thing, right, to have all of the Zariski dense closed points living in these multiples of the index, as long as you're large enough. I guess I could kind of believe it for the curves just because I was going to say just because of some intersection theory nonsense, but I don't actually know if what I'm thinking makes totally logical sense. All right, let's move on. So far less is known when the dimension of x is at least 2. In this paper, we initiate the study of Zariski density of algebraic points on surfaces in a case that builds upon our understanding for curves. Primary case is the product of two nice curves. The structure is constrained by the structures of delta and delta for C and D. If the genus of one of the curves is at most 9, so an upper bound, then the product of these two sets, which I guess you'd take pairwise products, is contained in the density degree set of this two, and that's contained in the intersection. It's kind of strong constraints. I guess sometimes for like products of curves, there's some properties where there's like these weird diagonal curves that sometimes mess a lot of things up, but let me think if I can even make sense of why I would think this is true. So, if the genus of one of the curves is at most 9, the genus of one of the curves is at most 9. Okay, then what's this? So, this is the set of degrees for which you have points of that degree are Zariski dense on C. This is the same for D. So, definitely, I guess I can take like a dense set of degree D points here and a dense set of degree D points here. And then it has to be degree exactly D. Okay, let's assume that these are, I can get some Zariski dense set which is irreducible, and then I can, like each of the points is irreducible for both of the curves, and then also their compositums are kind of disjoint, linearly disjoint. So the two fields are linearly disjoint inside some algebraic closures so that the compositum is like maximal degree. Then that would be kind of what this is. Right, and so this is saying that you could get more points that are Zariski dense, or more degrees in which you get Zariski dense points than just that case. And then this one is saying, oh, but it's contained in, so what could happen is something like, what could happen is like if you just took C and C or something, like C times C, then the delta set here would be like whatever this is, right? Kind of multiples of the index, at least if you're large enough. And then this one must be the same if, okay, but maybe it's not exactly the same. No, that's kind of clear actually. If it was like C times C, because then you could have like F tensor over the base field K with F. That should look like okay, like let's say that it's Galois, right? Then you'd expect to get some Galois number of copies of F, but in general you should expect to get what, at least like one copy of F and then some other stuff. I don't really know. I don't remember. You should expect to get at least one copy of F because F tensor over K with F probably has a multiplication map to F itself. Okay, so I'd expect that if you had like C times itself, then this set kind of makes sense. Why you'd have this on the right as an upper bound. And then in general, I guess you can also get this. It's weird that the genus at most 9 condition comes in. How would that come in? Genus at most 9 is such a strange condition. The upper bound still holds. The lower bound depends on the degrees of P1 parameterized points. No, I kind of believe this. Is this maybe this is something to do with like irreducible field extensions? I'm gonna go check. I don't know. Can I look up irreducible? Maybe it has nothing to do with that, but I was kind of thinking you'd have to use some Hilbert irreducibility theorem at some point, but all right, still not quite sure, but it's what my gut tells me. Okay, so asymptotically, it is known that for any nice variety X, the density degree set contains all sufficiently large multiples of the index. It's all sufficiently large multiples of the index. Whose paper is this? Okay. This result is not effective. Although it is known that for any nice variety X, the density degree set contains all sufficiently large multiples of the index. Can I understand that? Let's think. I think I can't get it. Yeah. I don't know. Yeah, I'm not sure. Our first result is an analog for X as the product of two curves. For simplicity, we state the result in the case that C and D both have a K rational point. The general result is theorem 3.6. Let C and D be nice curves over K. Generis GC and GD. Assume further that both C and D have K rational points. Then all of these integers live in there. This is some insane music. Alright, we'll keep listening to it. And so long as you have a high enough degree that the set of those points are just dense, huh? If the genera is small, then they can sharpen this containment using explicit geometry or low genus curves. As above, we state our result when C and D both have a K point. Suppose that C and D are nice curves of genus GC and GD, and assume that C and D both have K rational points. Interesting set of numbers. 2, 3, 5, 6, 7, 9, and 11. No 8 and no 10. 2, 3, 5. No 4 either. I just kind of missed that. No 6 here. The method of covering the surface with curves and applying the previous strategy, which relies on the Riemann-Roch theorem, is impractical or impossible. Oh, wait. We've got to read the theory. So to prove theorem 1.1, we construct explicit collections of curves on X gamma, a bounded genus. We construct explicit collections of curves, some family X gamma maybe, of bounded genus in C times D, passing through fixed sets of closed points, and such that their union is dense in this surface. Consequently, applying the bound 1 on each curve, we conclude that for any D greater than or equal to 2G, the surface has dense degree D points. Right, so these are bounded genus. Okay. Right. Bounded genus where all of the fibers have some. Right, so can you... The genus is upper semi-continuous, so there's basically they all have some fixed genus. Okay, so that's what this is. It's not upper semi-continuous. Is it lower semi-continuous? It is upper semi-continuous. I'm just doing a little bit of a degeneration thing, right? A genus 1 guy can degenerate to a genus 0 guy. Is that true? Or in a flat family, they're all just constant? I know that I just looked at this, so I want to say if you have I know that the dimension function for cohomology is upper semi-continuous for flat sheaves. And so on some, but also I know that the Hilbert polynomial is constant on flat families. So if you have a flat family of curves, then so long as they're I want to say connected, but I'm not exactly sure of all the exact statements that I need here. Okay, but I get that there's going to be at least some open dense thing where they all have the same genus. But probably maybe they even have. No, I'm just going to move on from there. So consequently, applying the bound on each curve, we conclude that for any d that's greater than or equal to twice that, the surface has dense degree d points. Yeah, that's really neat. We construct explicit collections of curves of bounded genus. Yeah, so how would you do that? I mean, you could do something like this is a stupid way to get curves, I guess, which is just like embed this into some large dimensional projective space, then take linear sections. And then generically, that's some smooth curve, and it's going to be of some fixed genus. So that gives you something. Is this related to 3g d 3g, so 3g d squared plus gc plus gd times 2. I don't know what kind of function you'd get. I would expect you'd get some kind of polynomial function from the construction that I said, but maybe this is like significantly better. To prove theorem 1.2, we both construct lower genus families and exploit the fact that one can be sharpened with more explicit knowledge of the divisors on this family. Okay. Small degree points, applications to non-product surfaces, and then outline. So, let's see. So small degree points. The method of covering the surface with curves and applying the previous strategy, which relies on the Riemann-Roch theorem. The method of covering the surface with curves and applying the previous strategy, which relies on the Riemann-Roch theorem, is impractical or impossible for points of very small degree. Instead, we construct these points by pulling back points from other varieties, which requires proving density of rational points on surfaces. Instead, we construct these points by pulling back points from other varieties. So you get like maps from C times D to like, I mean, you get a map to C, for example. You can pull back points from C. Is that the idea? This is quite difficult and entangled with several deep conjectures in number theory. I believe that. For example, we show in theorem 5.10 that the parity conjecture sometimes implies that 3 is in here when GC is 1 or GD is 2 and GD is 2. For quadratic points where they both have, where C and D both have genus bounded by 2, we consider the quotient surface where I is a hyperelliptic involution. I guess I don't know what that means if the genus is 0 for both of them. Oh, maybe you can still get a degree 2 cover up P1, so maybe that's just what the statement is. Since C times D to S is a finite map of degree 2, if 1 is not in there and 1 is in the quotient, then we can conclude via pullback that 2 is in there. In fact, if the Jacobian of C and D both have rank 0, meaning that they have a torsion subgroup of rational points only, I guess. the density of quadratic points on C times D can be reduced to the density of rational points on finitely many surfaces of this form. Okay. In low genus, the surface S has interesting geometry. When C and D are elliptic curves, right? S is a cumulative surface associated to the abelian surface C times D. When one has genus 1, one has genus 2, S is a quadratic twist, elliptic vibration over P1. Conjecturally, all such surfaces have dense rational points. In section 5.1, we give some examples when this conjecture can be verified. Lastly, when they both have genus 2 and the surface is of general type, and the Bombieri-Ling conjecture predicts that it does not have. Lastly, when both C and D have genus 2, the surface S is of general type, and the Bombieri-Ling conjecture predicts that it does not have dense rational points. So, but they still get a lot of these degrees somehow. So in proposition 6.10, we give an example based on an idea of Adam Logan of genus 2 curves where the degree sets are both 2 times n, for which 2 is not in this thing, despite the fact that there exists degree 2 points on C times D. Yeah, that's really interesting. This is actually a really interesting statement, right? I mean, it seemed like for higher degree points, this doesn't happen. Like if you have a degree n point and n is large, at least for curves, right? This statement says that then they're just dense. And I kind of believe that based off of like purely kind of the fact that for the curve case, you can get some line bundles from these points and their multiples. And like if you have like 2G, then the line bundles are going to be okay, honestly there's something about G in my mind here, but if you have at least 2G, then I thought it was like 2G minus 1 or 2G plus 1. One of those makes it very ample, so then you get like a very ample embedding from curve to projective space. And maybe you can take so how do I get a bunch of degree D curves? I was thinking the degree of that embedding is the degree of whatever the point they used was, or of the multiple of the index. So you can like project down to a P1, and then you can use like okay, so now I want to say something like if you have one irreducible fiber, you've got infinitely many irreducible fibers. I think that must be true if all the fibers are geometrically reduced. So I think that's kind of how the curve case is done. But it's interesting that you can basically say that fails for surfaces. So this is an interesting example. On the other hand, when pick 0C or pick 0D has positive rank, right, and this is also for low degree points, but anything that you can say for surfaces is interesting. I'll just say that because they're not as intimately tied to line bundles. There can be additional sources of quadratic points. Why is that? Let me think. Come on, I'm just going to read it. Okay, so for example, we show in proposition 6.5 that the quadratic points
are dense on a self-product of a genus curve, 2 curve with pick 0 of positive rank by pulling back rational points from pick 0. Positive rank. Oh, I was gonna say maybe there's something. Well, okay, so I guess they probably just embed C into pick 0, but I was kind of gonna say maybe actually there should be like a birational map, right, from sim2 to of C to like pick 2, and is that just useless? For a genus 2 curve, you get 2g minus 2, so you have a goddamn, you have a point of order 2. So pick 2 of the curve has a rational point, so it's isomorphic to pick 0. So you get a map from sim2 of C to pick 0, effectively, and then you can pull back these rational points. I believe that. So for example, we show in proposition 6.5 that the quadratic points are dense on a self-product. So that's the proof, right? It's maybe not quite so clear because you have to check whether or not... so I can imagine that there's some self-product of a genus 2 curve. I was just thinking that sim2 to pick 2 is... I don't even know if that's surjective, but I thought that it was. And then you have all these... You've got like an infinite collection, if it's positive rank, of rational points, and so you can look at their preimages. And this is some map which has, I think, like a really specific... It's like... Okay, this could be false, but there's like a birational thing for... it's probably birational, right? You have C times C, sim2 is a surface, and pick 2 in the genus 2 case is a surface as well. So I think it's birational. There's some explicit loci where it's not an isomorphism, and then maybe you can just say like okay, that doesn't really say anything about density, does it? First, we show that the quadratic points are dense on a self-product of a genus 2 curve with pick 0 positive rank by pulling back rational points from pick 0. Or maybe the map is something like you want to take P and Q, and you want to send that to P minus Q and pick 0. Maybe this is the map that they're looking at. I'm not sure. Yeah. All right. Yeah. Generally, I guess I don't. Maybe I don't have any idea. Although I kind of want to see. Okay. So let C be a nice genus 2 curve over K over K. Let pick 0 be the Jacobian. Then we get this. So 2 delta of pick is contained inside delta of C times C. In particular, if pick 0 is simple and the rank is positive, then 2 is in here. Why does this need to be simple for this statement? Is it for the nice statement or what? Oh, I think this is actually about, I don't know. I don't know, but I could imagine that this is about the density claim. But let's see. So, right, because as soon as the rank is, as soon as the rank is positive. Oh no, yeah, this is about the density claim. Because if the rank is positive, then you get some rational points, but there's no guarantee that they're dense inside of. There's no guarantee that they're dense, and so you don't know if delta is. If this delta set contains 1. Okay, but if it's simple, then it does contain 1. Okay. And so since the genus is 2, the Jacobian is an abelian surface, similarly to the proof, we can consider this birational morphism. Precomposing with the canonical map gives us a morphism, and there exists a non-empty open set such that the restriction is a finite morphism of degree 2. Oh yeah, so I was right, and I just forgot that the map C times C to sim2, which is I think how I started it out, folds in half. Okay, and so the hard thing is then just showing that like something about the irreducibility, I guess. Yeah. If a dense subset of preimages have degree 2D, then you're done. Yep. Otherwise, we conclude that D is in there. And if D is in there, then it must be also in here. That one, I guess I don't know why it's true, but maybe you've got a bunch of maps, so. You can either project, or you can consider, I can imagine the diagonal just missing all of them, so that doesn't really help. So I guess you have to project, and then the claim is maybe something about dense points of degree D implies dense points on the projection. It's almost believable, but I think there's some kind of subtlety there too, right? Just because if you have like some irreducible degree D point mapping to your curve, does that mean that it has that might actually do it. Yeah. That might do it. I mean, it certainly does if the genus is large enough, right? Since C is hyperelliptic, 2 is in there. And hence the lower bound guarantees that 2D is also in there, yeah. 2 is in one and D is in the other. I guess I believe this statement if D is large enough. Right, 2 times the genus. In this case, that's 4. So there's just like a handful of cases that I would be kind of confused about. I guess I could go through and check those. There must be something that's pretty obvious that I'm not seeing for that though. Just the projection maybe just implies that you have a dense set of points of degree D. Now if pick 0 is simple, and then we're done. Right, okay. So let's see. Where were we? Some of the arithmetic complexity is eased by considering the potential density degree set. Recall that for variety x and integer, D is in the potential density degree set. Weierstrass P of x of k. If there exists a finite extension for which D is in this density degree set over k prime, and x can also be considered over k prime, unless you have to base change up or something. If x is c times d, it's product of two curves, genus 0 or 1, then this is just equal to that. C specifically has genus 0 or 1. Genus 0, guess that's clear. Genus 1, I guess I kind of believe that too. If this is base change, which I guess it is. In the case of products of genus 2 curves, we give a nearly complete description of the potential density degree set in theorem. We give a nearly complete description of the potential density degree set in theorem 6.15. All right, let's take a look. I think this is kind of funny. N greater than or equal to 2 without 2, 3, or 5. Because couldn't you just say n greater than or equal to 4, not 5? All right, let's go back to 2. Now, applications to non-product surfaces. One of the main reasons for studying product surfaces is their close relation to the more well-studied setting of curves. Another reason is their closeness to several other interesting families of surfaces, like the K3 surface from before. So our methods and results can be applied to principally polarized abelian surfaces. I guess I believe that. Maybe there's some finite covering by elliptic curves or... and of bielliptic surfaces in particular. In both cases, we make use of the fact that they are covered by products of curves. One subtlety is that the image of a degree D point on a finite map may be a smaller degree point. That's why I was confused about the projection thing. But maybe it's because you take the point, maybe if you have a degree D point, I don't know. Yeah. To circumvent this issue, we utilize constructions of points where we guarantee that the residue field is a primitive extension of K. If ever K is an abelian surface such that that is isogenous to a principally polarized abelian surface, then n greater than or equal to 3 is contained inside here. Furthermore, A is isogenous to Jacobian of a genus 2 curve. Then 2's in there. So let S be a bielliptic surface over K, where g acts on E1 via translations by k rational points, and on E2 such that E2 mod g is P1. Be a bielliptic surface over K, where G acts on E1 by translations by K rational points, and E2 is such that E2 mod the group action is P1. This is kind of like an Aguza surface. That's what I want to say. Then you get this thing. One of the main properties of the density degree set of curves is that it is closed under multiplication by positive integers. Whether the same property, oh yeah, right, set for curves. Whether the same property holds for higher dimensional varieties is still unknown, but I believe that if it's not easy to prove, it's false. However, in many cases that we consider, our sharp description of the density degree set implies that it satisfies this multiplicative property. Which, I know that just totally contradicts my prediction that it's false, but I guess this is a more general thing that I could think, okay. I want to say, I could see something like this being true. Where you get like all but a finite number. And a lot of these say that it's all but a finite number. Can I think of a reason why it would be false? Okay, maybe it's true. I don't know. No, I don't think it's going to be true, but... Yeah, I'm not sure. I wonder if you can get, I mean, I guess I just wonder this. Like, I wonder if you can get like a general type surface or something like really ugly, which has like a finite number of k rational points, such that like no curve lies on those k rational points. Is that even possible as a statement already? And then like no curve lies on those points, then no curve lies on all of those points, then is the Zariski closure of those points all of the surface? I guess not. I guess you could always, I guess you have to have infinitely many points. Just because of, you could probably put curves through all of the points, and then you have just finite number of points. So you need infinitely many points. So you need infinitely many rational points. I want to say, like, I wonder if you can get an example where like there's just like a dense set of rational points, but then there's some point missing, right? It's an interesting question to just say, like, if there's a dense set of rational points, does this imply that there's a dense set of all degree points? And that might be true, but I don't know. And that's like implied by this, right? Yeah, I don't know. It's cool. All right. Boom, back to this. Une remarque sur on. Okay, I'm just gonna read it in English. On a remark on the ARF invariant. An alternative construction using Witt's formalism of the ARF invariant of quadratic forms characteristic too. Quantum K theory levels in physics and math, non-commutative resolutions, and pre-quotients of Calabi double covers. Leschetz decomposition over Z and applications. On the conjecture of Kashuba and Matthew about free Jordan algebras. On multiplicities and length spectra of semi-arithmetic hyperbolic surfaces. Sums and products and sets of positive density. Gushel-Mackay varieties. And I kind of want to close after getting to this part, but sometimes it's kind of interesting to see like what people have updated. Okay. So there's a couple things that we can do, but there's like a thing, there's at least one thing that I kind of wanted to do. And then I kind of got demotivated from thinking about Oscar Oscar at all from last time. Which is like, we're eventually going to get to this, right? But one thing that I have to do is, download, yeah, so I have to do like multiple, if I want to develop in this, I have to do like multiple, This was another thing that I actually wanted to do. So, was do something with the group cohomology. Cohomology group Z0, Z1. Z is G module, AH, H is HOM, VVM. VVM is this matrix. H is this thing, and A is symmetric group. So G module, symmetric group, H. I don't know what that means. And then you call the cohomology group of... Oh, this G module. Oh, yeah, you're looking at H as a G module under A. I don't know about that. This seems weird. Okay, so what do I want to do? So one thing that we found out, right, is that in M2, there is a package. So one, I had to update. And I could have done that incorrectly. Not sure. But I had to get a... I had to get the package update. I had to update so that we could access some parallelism. So I'm gonna go to top on this screen just to check if anything's gonna come up in this that I don't want to be shown. I think we're good though. One thing that's insane is just, this has gotta be Google Chrome, right? Oh, OBS, that makes way more sense. I was like, there's nothing running on my PC, so like, what is actually taking up the most? Seeing Xorg there is also kind of crazy. Right, and so looks like we've got a 1 average, load average. I mean, should we be able to get it up to 24? I don't know. I think that would be, I mean, I got 24 cores on the CPU, so I think that would be the theoretical max. It was like 24, which probably wouldn't be able to see. But we have some code. Ugh. Meant to do this, but alright. So I think that this is something. So we're gonna try it. See if it terminates while I'm working, or if I can even run it while I'm working. I imagine that this is gonna go fucking terribly. So this first guy, it's going to try to compute a saturation of an ideal, and we're going to monitor how much CPU usage that's taking. I think that it can go as high as 1200, but I'm curious when I'm actually using things like OBS and Xorg, how many threads I'm... Oh, wait. This is going to take a little bit. I want to stop it. And clear that and start again. So this one. These guys. Oh, I actually could have left that. What I was thinking was that the last time that I ran this, I didn't have the allowable threads, so I forgot that I changed this option. And so, okay, so what this is doing is that it's effectively trying to compute this saturation of this ideal. And to use parallelism in Macaulay 2, I had to use this msolve saturate function, which means that if you want to do a saturation of an ideal in like a graded ring, so for like some projective variety, then you have to lift the ideal up to actually just the polynomial ring. And then this msolve saturate, it's a function that allows you to do Grosvenor basis over finite fields in parallel on your machine. And the number of threads, I gave it the allowable number of threads, which I had also increased, I thought, to max allowable threads. So for Macaulay 2 on my computer, it says that 17 is the maximum allowable threads. My computer supports 48 threads, which means that I think that we're still actually doing kind of okay as far as CPU usage should be concerned. And then when I wasn't running OBS or, you know, some of these other things, I was able to get the CPU usage up to 1200. So I'm curious about how it'll go.
Oh, Megami. What's up, bud?
So it fluctuates kind of a lot, which is interesting. Right, like 2 cores, 3 cores. It's like right now it's using 3 cores, 4 cores, 5 cores, 3 cores. I don't know why. I think that's super interesting. Okay, so could probably write the rest of this. What I want to do is consider T, which is going to be intersect of all of these guys. I'm mainly just trying to check if this is faster and gives what I would think is correct answer for this computation. I think I was thinking about it earlier, and basically I want to saturate an ideal with respect to the irrelevant ideal, but doing that on my machine is like kind of painfully slow. In a lot of cases that I'm actually interested in. So this is like a test case to see if we can parallelize it. But you have to like lift the computation and then project it back down. And so we need one more thing, which is like in Macaulay 2. We need to check out what an image of an ideal is. So I think I guess I can just take okay, so like this, that was kind of quick. All right, let's try the next one. It's interesting that it returns a matrix. The matrix is presumably giving us our like Grosvenor basis for this ideal. But I want to say that's problematic just because I need to take the co-kernel, I would assume. So what is the type of a matrix in Macaulay 2? So we technically want the image of these matrices. Summed up. Sorry, hanging out with the cat. Well, I mean, I'm not really sorry for that, but we're running this thing. I'm gonna think about what I would input to get like direct sum of modules, but it's not direct sum, it's like sum of modules into the thing. Let's go. All right, next one.
join me? You want to get up here? You're not really a lab cat, are you? I can pull out the Macaulay documentation that I'm looking for, so we're not looking for direct sum, we're looking for like literal sum. So sum of modules. To compute the sum of submodules, use the plus operator. Make sense? Yeah. Not listed though, right? I mean, matrix plus matrix. Unary or binary? Yeah, I don't want to do that. I'm on matrices, that's the problem, huh? Let's do submodule. Boom. All right. My friends would say that we're juicing. So each of these images, right, I'm not even taking the sum, am I? I'm actually intersecting. Intersection of submodules. So intersect submodules. So here we've just got to go next. We'll do T0 is image of we're going to try to do image of matrix, so matrix type again. What was it again? Just image, right? So, and that's a module. Yeah.
So image of S0. I should make this I0, right? Let's do that. We'll do M0. And then we'll do that a bunch of times. This is kind of why I wish I learned how to use Vim, or I even think about using Vim, because I know that didn't take me long, but I get there's like a macro that I could have used to do that. Now each of these is a submodule. I got to take the intersection, so we'll do int ideal. It's going to be intersect m0, m1, m2, m3, m4, m5. And we'll just do T ideal, S ideal. It's like the intersection ideal. Just afraid of an overlapping namespace at all. Intersection ideal, it's gonna be this. That's what we need. And now we need to look at the image of this ideal inside of, so this is an ideal in R. And now I want to look at it in the quotient S. So, ooh, this is looking kind of juicy. I actually don't remember how long the original computation took, so above this line, but I don't remember it taking that long. So project submodule to quotient ring. I think maybe, is there a module to ideal function in Macaulay 2? An ideal I is also an R submodule. In Macaulay 2, we distinguish when we are thinking of I as an ideal or as a module. It is first defined as an ideal. It is easily turned into a module. And for any submodule of the rank 1 free module R, we obtain an ideal of the generators using the function ideal. So if you have a matrix, you can take the image, and then you can take the ideal of that image. Kadook. And then what? Trying to wonder if it's faster. I mean, I'm trying to wonder if there's any benefit in doing like changing each of these images to ideals and then intersecting. I can't imagine that there would be benefit, but let's see. So once we have all of these, we've got the intersection ideal. Now we need to figure out how to go from quotient ring Macaulay 2. I think I probably just mod out by the thing. You can define ideals within a quotient ring and perform operations on them. So creating quotient ring, like this almost feels like it's stolen from something. Just saying. So, CPU memory, 1700. It used all 17 cores. It's capping out. That's crazy. I mean, that is crazy. And now I'm actually kind of confused. 1700% CPU usage. Is CPU use? So, is CPU usage in Linux based on core or threads? In Linux, CPU usage is primarily reported and managed based on threads, not just cores. While each core can execute instructions simultaneously, it's threads that represent the individual sequence of instructions being processed. Linux distributes processes and threads across all available cores to maximize CPU utilization. That is crazy. And now we do the physical assessment with my hand. So the CPU is noticeably hotter. Although totally, to be honest, I mean, that could be the GPU. I've seen it turn on a couple times just streaming so far. Maybe to do with the, I don't know, something to do with the stream, maybe. Everything has been running very smoothly, though, even considering using 17 threads. This just went down. I wonder if that says that. No, then it shoots up to 700. 1700. I don't know if this is the same process. That's so nuts. To me, and there's still 31 cores, not 31 threads not being used. I mean, okay. Actually, it's not true that there's 31 not being used. There's like 17, and then like 1, 2, so that's like 18, 19. And even if these are all almost on different processes, then it's like 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. And even there's like, these are all in the same, right? So it's crazy. Right, so we want to look at the ideal inside, I guess, yeah, I mean, let's look up image of ideal in quotient ring, Macaulay 2. Boom, and we move on, so that was S5. We can just copy these ones. They're all going to be immediate. And we take their intersection. And that was immediate. And now we need to, now's the thing that we need to, okay, so. I kind of just think it's going to be something like this. So let's do intersection ideal. Let's do n int ideal equals intersection ideal times s. And I'm gonna just ideal of s, okay. And the last thing is, can we take a Hilbert series? So now I need, let's just write the whole thing again. So Hilbert series n int ideal. Actually, did we include depth as a package? Nope. So it needs package depth. Let's just try to calculate the depth of this module. And then I'll figure out what Hilbert series I need. So I think that I should have used 5, so 9 in this case. So it should be Hilbert series of n int ideal order is going to be 9. And then the question is, what am I going to get for an answer, right? And I remember getting 8, but there's no guarantee on that. There's no guarantee on that value, actually. Okay, so let's just double check. And we've double checked, I guess. So what do I expect? If everything has been correct so far, then this should return 2. It should be depth 2. And when we calculate Hilbert series of this n intersection ideal to order 9, then I think that we should get something like 6 or 8 for the value of the degree 8th coefficient. It's kind of crazy how long the depth computation takes, honestly. I mean, it's not using 1700% CPU. That's the first issue, right? Yeah. So if this experiment works, then what we need to do afterwards is to go through this file and basically translate all of these. I think actually this first one was completed into this language. There's a couple of other examples actually that I wanted to try out. From here on things that I think are actually like fast to compute, like this one, right? It should be like fast to compute. But on the other hand, using small number is kind of interesting. It's interesting to me that like, so msolve, the parallelization package for this Grobner basis calculation, it doesn't allow values less than 2 to the 16th, or greater than 2 to the 32, maybe 2 to the 31, I can't remember. And the second of those makes sense to me, in just the sense that like, you know, see things for whatever reason using ints and the way that they are like coded. I get 32-bit. Okay, that makes sense. The 16-bit minimum is the thing that I think is weird to me. Yeah, is it because of floating point operations? I mean, that would be, in my mind, insane. Anyways, this is still running, huh? How am I supposed to get rid of this upper part now that it's gone? Just do that. So I think, yeah, so I think I ran this like overnight last time, which was a surprise to me, but I think that's how long it took. I don't know if I actually had to turn this into a module first. I don't know if it did anything. The thing that I was worried about was that calling depth on an ideal would do something like calling depth on arm on the ideal. So there's two major groups of routines, one for finding the depth of an ideal or module or a ring, or the depth of an ideal on a module, and the other for finding relatively sparse systems of homogeneous parameters inside an ideal. The depth of an ideal on a module is fundamental invariant, kind of arithmetic version of codimension. In many local or graded cases, one is interested in the depth of the maximal ideal on the module, and then we speak just of the depth of the module. Over a regular ring, depth is most efficiently computed using the Austin-Buchsbaum formula, where projective dimension is pdim. And then in general, the depth of an ideal on a module is the minimum of some non-vanishing x groups, diminishing minimal degree of non-vanishing x. Depth can be computed from regular sequences, which are systems parameters. The other routines in this package try probabilistically to find relatively sparse systems parameters. The maximum length of such a system is equal to the codimension of the ideal. Without further arguments, look for regular sequences of length codimension I. I feel like this could go faster. I just need to know that the depth is at least 2. So it should be easy to check that. I feel like it would even be easier to some extent to just like pick a random element and then pick a random other element. Okie doke. Let's check how this function works. Doesn't really tell you, huh? It worries me because, I mean, well, it worries me because the system of parameters says that it runs a Grosvenor basis, which I just spent like, okay. Worry vanished. Right, now let's take this Hilbert series. And what do we get? That was not what I expected. So why was it not what I expected? 217. See if we can make sense of this. Okay, so let's see what we did. So we got ring, R, ideal, R mod I. Just Nothing crazy yet. I'm 100% sure this is the right ideal, because we had to go back and check it. We got F4, which is proj S. We take 9 ideals. That's fine. We create these ideals. And this one. The ideal. This is something that I'm a little bit not sure about. Is that somehow the ideal in my mind, so we can do this, but it's not clear whether this is going to do anything good for us. So the ideal in my mind, let's do divisors package. So I want to know if I can basically take a ideal to a divisor. Yeah, it looks like I can. So we do F15. So let's do FF15. Let's do FDiv 15 equals divisor of F15. And let's do right, that's what I thought. Yeah, I don't have to say anything else. Okay. And so then we lifted. Did we do that? We lifted this ideal to R. And we lifted all of these guys to R. Then we saturated all of these guys. Hey, Megami. After saturating, we took an intersection, hoping to find out if so this is the one thing that could be totally false, which is like intersection of saturations of ideals. Is that a intersection of saturation of ideals? Alright, so let's see. So what I really want to see is something like, I mean, I could just think about this, which is probably what is going to end up happening. Whoa, Chacho. Cat City. Hey, bud. Oh, Jesus Christ.
coffee shop. But when I see you smile, here you seem alone. I know it's where my heart belongs. Freshly brewed and iced, oh, tell me, won't you try this melody I made for you? So gently beat the sweet milk, cream and coffee meet. We've always got enough for two. 'Cause all the different flavors love to come together. Somewhere they can always play. These doors are always open. Come enjoy the Hope Cafe.